Hello, everyone, and welcome to the first lecture of Physics 150, General Education of Physics for Non-Physics Majors. I'm your instructor, George Kutrakan, and I will be guiding you through these lectures with recorded videos for the duration of the course. Today, we're going to start with the first lecture, uh, which will start in chapter 2 of the textbook that's being assigned for your reading. It is by Paul Hewitt, and we'll be using his book throughout the course. To begin this course, we're going to start in chapter 2, which begins with the first of Newton's three laws of motion. So we're going to discuss these one at a time. And in this chapter, we will look specifically at Newton's first law. Okay, let's get started. Let me first do an overview of what we're going to cover in this chapter. As you can see on the list from the slide, we are going to talk about Galileo's concept of inertia, Newton's first law, net force and vectors, the equilibrium rule, which has to do with the concept of stationary objects being held in their place by opposing forces, for example. We'll talk about support force, the equilibrium of moving things, and finally, the moving Earth. Now, the first thing to notice here, or that we're going to talk about, is that the first major inroad in or understanding of objects and how they move can be traced back to Galileo. And many of you are familiar with his famous experiment at the Leaning Tower of Pisa, where he dropped two objects, one a very light object and one a very heavy object. And the observation was that they, in the absence of air resistance, or accounting for that in some way, or neglecting it because they were both very, very small amounts of resistance, that the objects arrived and hit the ground at essentially the same time. Now, the reason why this is important is that when what we're doing in physics, or the question we are asking is, how do objects change their position in time, and how do they change their speed or velocity in time? So in order to be able to predict this, we need to know laws of motion that were created. And one of the first understandings of this came from Galileo. In his example here, we use the weight as the force of gravity. And so weight is generated, or it can be equivalent to the force of attraction to the Earth's surface. And he used that, of course, as a force. Now, the reason this was perhaps viewed as strange at the time, this observation that they both arrive at the ground at the same time, is that one was much heavier than the other. And so people thought, well, the heavy ball should arrive quicker or have exerted more force on it than the lightweight ball. And indeed, that is in fact true. But what we now know is that the quantity called acceleration, which is the change in velocity divided by the time over which that velocity occurs, that acceleration depends on the force divided by the mass of the object. And we'll talk more about what mass is in a minute. But mass is related to the intrinsic number of atoms in the object, with each object having a certain number of protons and neutrons and electrons. And so the force divided by the mass is the same for those two objects, and therefore they experience the same acceleration. Now, at the time of Galileo, we didn't know that yet, so it looked like a very strange effect. The second thing is that a moving object needs no force to keep it moving in the absence of friction. So this was another conclusion that Galileo's experiment saying that basically that if you have an object that's traveling at 5 feet per second, that if there are no forces acting on it, the object will continue to move at 5 feet per second, and therefore it will continue on indefinitely without as long as there are no forces either causing it to accelerate or frictional forces causing it to slow down. The other points that are worth pointing out here is that, in terms of Galileo's concept of inertia, is that he regarded force as a push or a pull on an object, and of course, it's still true and valid today as well. Inertia is a property of a matter to resist changes in motion, and it depends on the amount of matter that occurs that the object has, or what we call its mass. One way to look at this is, for example, that if we have a heavy Mack truck moving down the expressway at 70 miles per hour, it takes a lot more force to slow it down or bring it to rest than, say, a Volkswagen Beetle, which or small car or that is also going at 70 miles per hour. It takes much less force to slow the car down, or braking force, as we would say, to slow it down. It's much easier to slow down the low mass object than it is to slow down. It requires much less force to slow down the low mass object than it does to slow down the high mass object, which in this case we were talking about is a Mack truck. So this concept of inertia is resistance to change in its speed, and obviously, as we've said, the Mack truck has a great deal more inertia, and therefore it requires a great deal much more force to slow it down. One of the other important observations that Galileo made was the motion of objects on rolling objects on a inclined plane, such as the ball you see in the figure. And there were several observations he made that are very important. Balls rolling on downward sloping planes will pick up speed. That balls rolling on upward sloping planes will lose speed. And a ball on a horizontal plane maintains its speed indefinitely with the same velocity that it has. And furthermore, that on the horizontal plane, if it does come to rest, it is not because of its intrinsic nature, as Aristotle said, but it is due to the force of friction. Okay, on this slide, I'm going to let you answer the question when we get to these type of slides, and let you do your own self-examination or self-testing. You can look at these multiple choice questions and come up with answers based on the previous slides. Hopefully you'll be able to answer this one fairly easily, and I'll let you look at this with his answer, and we'll resume on the slide number 8. Okay, so now we are able to state firmly what Newton's first law of motion is. It states that every object continues in a state of rest, or it will remain in a state of uniform speed in a straight line unless acted on by a non-zero net force. So by net force, we mean that the sum of all forces acting on the object must add up to 0 if the object at rest remains at rest, and if the object moving at uniform speed remains at uniform speed. In fact, that's one of the ways we know that there are no other forces, or there are no net forces acting on the particle or the object. So this allows us to state very explicitly what Newton's first law means. Objects that are in motion uniform speed will remain at uniform speed, and objects at rest will remain at rest as long as there are no net forces acting on the particle. And what net force means is what we mean by this is the sum of all forces. And in particular, we're going to look at the vector quality of force, and we will say that the vectorial sum of all the forces must add to zero if the observation of Newton's first law is observed. And so we'll now discuss vectors in the next slide, and we'll move on to that in the next moment. So we said that that the force was a vectorial or a vector quantity. So we'll describe now a little bit about vectors. So first of all, a quantity whose description requires both magnitude, which is how strong is the force, which is magnitude, and which direction is the force acting on the object. So it has two quantities associated with it, magnitude and direction. And those two quantities can be represented as an arrow drawn to the scale. And these are called vectors. So the drawn to scale simply means that if I have two forces acting on an object, one is 2 pounds to the right and the other one is 1 pound to the left, then I can add them vectorially by drawing the first force as an arrow that's 2 inches long, where 2 inches represents 2 pounds, or 1 inch of vector length on a piece of paper represents 1 pound of force. And if I draw these two vectors, I'll have a vector going to the right at a distance of 2 inches, and with the arrow pointed in the direction at the right. And then I'll have a force of 1 pound to the left, and so I'll have another arrow pointing to the left, and the net result will be 2 minus 1, which is in that case a net force of 1 pound. We'll have an example in the next slide. So here we have an example of two forces acting on an object for two different scenarios. One in which I've got, we will say, two people pulling on a brick with a force of 5 newtons. Now we will discuss the concept of a newton in a later section, but for now, we just remark that the newton is a metric quantity of force, and it corresponds to a force of about a quarter pound, or we would say about 4 newtons is equivalent to 1 pound. Slightly more than that, actually. It's about 4.5 newtons is a pound, but that's gives you a ballpark idea. So if we have two forces acting on it, one is 5 newtons and the other one is 5 newtons, and these two people are both applying that same force to the right, then I can describe each force as a vector, which has a arrow represented by an arrow with a length that is representative of the amount of force. So let's suppose that I choose my scale so that on a piece of paper, 1 inch is the same as 1 newton of force. So if I want to represent 5 newtons, I need to have a length of an arrow that is 5 inches long and pointing to the right. If I now want to add that force to another force, which is also 5 newtons, well, we obviously can add 5 and 5 and get 10. But the other way of seeing it is that the length of the arrow of the first force gets added to the length of the arrow of the second force. So I do that by placing the tail of the second force at the head of the first force, and I now extend the length of that arrow to be 10 inches, which corresponds to 10 newtons. So that's a vectorial way of representing how I add forces by a vector or an arrow that I can draw on a piece of paper. And we set the scale to decide how many inches is going to be equal to 1 Newton, for example. So in this case, we chose 1 inch equal to 1 Newton of force. So a 5 Newton force would be represented by a 5 inch long arrow. Now, in the second example, what we see happening is that if the forces of 5 Newtons are applied in opposite directions, then the vectorial sum of those two forces adds up to 0. And that is, of course, the net force of 0. And that's the condition we talked about in Newton's first law. If there is no net force, then the object will either remain at rest if it was initially at rest, or it will remain in uniform motion if it was initially in uniform motion before those opposing forces were applied. But as long as the sum of the forces is 0, the speed of the particle or the object is not going to change. Okay, so I hope you can begin to see then how to add vectorial forces when we we draw out the force one at a time. We draw out a length of an arrow with a tip on the arrow, and the length of the arrow is the amount of force drawn to scale. And then the second force, we place the left end of the arrow at the tip of the first arrow and draw another vector that will extend it to a new point in space, which in this case, in the first case, will be a vector that is 10 inches long when we add two 5-inch vectors together that are in the same direction. And that gives us a way to vectorially add these quantities. Now, this slide is really just a review or repetition of what we've already said. We have vector quantities and we have scalar quantities. The only thing I would add is that the scalar quantities, in this case mass, volume, and speed, are all positive quantities. You can't have negative mass, negative volume, or negative speed. Those quantities are all positive, and those are called scalars, whereas the velocity is a force and acceleration are all vectors.